While we've talked about a lot of possibilities for solutions to differential equations, there are even more possibilities. So one possibility is that there might be a series solution to a linear differential equation. We're going to be talking about that. But before we get into that, we need to review some things about power series. You likely were introduced to power series at some point in your calculus career. If you weren't, then this lesson today is going to be incredibly important for you to dive in, to get the vocabulary, and start getting comfortable with this series notation and the ideas behind it. When we're reviewing power series, the first thing that we need to talk about is what is a power series? So a power series in x minus a is an infinite series of the form the sum from n equals 0 to infinity of c sub n times the quantity x minus a to the nth power. And if we write out the terms of that sum, we'll substitute in 0 first, so we'll get c sub 0 times the quantity x minus a to the 0 power. Well, anything raised to the 0 power is simply 1, so our first term is c0. Then, if we substitute in n equals 1, we'll get c sub 1 times the quantity x minus a to the first power. Subbing in 2, we get c sub 2 times x minus a to the second power. And we would continue doing this forever and ever, since we'll never actually reach a value that we call infinity. So that's what a power series is. You probably, when you were first introduced to them, whether that's now or in the past, are thinking this infinite sum can't possibly be useful. Well, it turns out it really is. And there's some properties about power series that we can use to help us. So, first thing we need to talk about is the idea of convergence. A power series is convergent at a specified value of x if its sequence of partial sums, we write that with a capital S sub capital N of x, converges. So what that means is if we take the limit as capital N approaches infinity of our sequence of partial sums, it's going to be some finite value. So it's going to exist. If instead that limit does not exist at x, or it goes off to infinity in some kind of way, then the series is said to be divergent. One thing that we like to know is where does the power series converge if it does? We talk about an interval of convergence when we're talking about this. So the interval of convergence is the set of all the real numbers x for which the series converges. And a, that value that's being subtracted from x in the series, is the center of that interval. To know how large that interval is, the radius of convergence tells us that. So we can find the radius by looking at the furthest, the min or the max of the interval of convergence and seeing how far it is from the center. So that distance between the min and the center, or the max and the center, those two distances will be equal, and they're considered the radius of convergence. Another term that we hear in relation to power series is the idea of absolute convergence. So in the interior of its interval of convergence, a power series converges absolutely. And what that means is if we put absolute values around everything inside of the sum, so we're only adding positive values to one another, that series is going to converge. This absolute convergence thing doesn't happen at the endpoints of our interval of convergence. A useful test that you've likely seen before is called the ratio test. It helps us know if a power series converges or not. So what we do is we suppose that our c sub n values are not equal to 0 for all n in our power series. And then what we look at is the limit as n approaches infinity of the ratio of c sub n plus 1 times the quantity x minus a raised to the power of the quantity n plus 1 divided by c sub n times the quantity x minus a raised to the nth power. So we're looking at the absolute value of that ratio, and we could simplify that and say, you know what, that actually equals the absolute value of x minus a times the limit as n approaches infinity of c sub n plus 1 divided by c sub n. And we assign that limit a value L. Now we're guaranteed that L is going to be a positive value since we're taking absolute values in this ratio and multiplying them together. So if L is less than 1, we say that the series converges. For it to be less than 1, what that means is that c sub n plus 1 is actually smaller than c sub n. So our series is converging absolutely. If instead L is greater than 1, that means that c sub n plus 1 is actually greater than c sub n as we move towards infinity. And that's telling us that the series diverges. And finally, if L equals 1, that means as we go to infinity, we've got some balance happening in some way, maybe. It's telling us that the test is inconclusive. So the ratio test is always inconclusive, actually, at endpoints of our a plus or minus r, so our interval of convergence around a. So now that we know some basics about power series, some basic vocabulary and figuring out whether things converge or not, we're going to move into some things that we'll be using as we work on solving differential equations with these things. So the first big idea is that a power series defines a function. That function is namely f of x equals y equals the sum n equals 0 to infinity of c sub n x to the n. This is simply the power series we've been looking at, substituting 0 in for a. And without that substitution, you could easily do any other power series and it would still be a function. So the domain of our function is actually the interval of convergence of the series. And if the radius of convergence is greater than 0, or it's infinite, then our function is continuous, differentiable, and integrable on the intervals a minus r to a plus r, or negative infinity to infinity, respectively. So whatever our interval of convergence is, whether it's all real numbers or some subset of the real numbers, our function is going to be continuous, differentiable, and integrable on that interval of convergence. Now, if we want to differentiate or integrate these things, it's a polynomial function. So we can simply integrate or differentiate term by term. And what I've done here is I've found the first and the second derivative of y, my power series function, that we started with. So in doing so, differentiating term by term, find that the first derivative follows the pattern of being the sum from n equals 1 instead of 0, because that first term is going to zero out since it's just a constant. So the sum from n equals 1 to infinity of c sub n times x to the n minus 1 power. You can see that we've done the derivative in there. We followed the power rule, multiplying by the exponent on x and subtracting 1 from it moving forward. So the first few terms are going to look like c sub 1 plus 2 times c sub 2x plus 3 times c sub 3x squared, and so on. Taking a derivative again, I'm going to take the derivative of my derivative function. And again, notice the first term is a constant, so it zeroes out. So we're going to start our sum at 2 now. So we have the sum from n equals 2 to infinity of c sub n times n, and now yet again we followed the power rule, multiplying by n minus 1 and subtracting 1 from our exponent on x. So we'll multiply times x to the n minus 2 power. So our first few terms will look like 2c sub 2 plus 6c sub 3x plus 12c sub 4x squared, and so on. So now that we have our power series function and we know something about its derivatives, we're going to talk about an identity property for a minute. So if we have a power series given there, our standard form, and it equals 0, when the radius of convergence is greater than 0 for all numbers x in some open interval, then that means that c sub n must equal 0 for all n. Next, we're going to talk about what it means for a power series to be analytic at a point. This definition will be very important as we move forward with the power series solutions to differential equations. So for a power series to be analytic at a point, f, our function, power series function, is analytic at a point A if it can be represented by a power series in x minus a with either a positive or an infinite radius of convergence. Finally, we're going to talk about doing arithmetic with power series. So power series can be combined through operations of addition, multiplication, and division. Notice subtraction is not there. That's because subtraction is simply adding the negative. So we could say addition, subtraction, multiplication, and division, and we wouldn't be incorrect here. So we can do all of this arithmetic, and we do it the same way. Notice this function is like a polynomial type function, so we do it the same way we would be adding, subtracting, multiplying, and dividing polynomials. The tricky part of this is that we have summation notation to deal with, and they're infinite sums, so we can't possibly write out all of the terms. So we need to figure out how to combine summation notation. And what better way to figure out how to combine summation notation than taking a look at an example? So we're going to take a look at an example where we'll be shifting summation indices. So notice here I'm combining two separate sums, and notice that one of them is a sum starting at 2 and the other is a sum starting at 0. Also of note is that the exponent on the x value in the sum is different in each of them. So one thing that can be helpful when we're trying to figure out how we should shift these is to take a look at what the first few parts of the sum look like. So the first few terms of my first sum are going to look like 2 times 1 times c sub 2 times x to the 2 minus 2, so to the 0 power. The next term will look like 3 times 3 minus 1, so times 2, times c sub 3 times x to the 3 minus 2, so first power. And finally, another term, let's go one more, we'll be plugging in n equals 4, so we'll have 4 times 4 minus 1, so times 3, c sub 4, x to the 4 minus 2, or second power, and then these keep on going. Now, I'm going to look and see what do the terms of the second series look like. So I'm offsetting them a little bit for a reason that will become clear soon, but let's take a look at the first term. Plugging in 0, I get c sub 0 x to the 0 plus 1, so to the first power. Then my next term that's going to be added to that, I'm going to be plugging in n equals 1, so I'll have c sub 1 x to the 1 plus 1, or to the second power. And then I'm going to continue this on till infinity. So notice the way I lined these up. I actually did it so that my x to the first power would be lined up, as well as my x to the second power, as well as my x to the 0 power. Since the second sum doesn't have an x to the 0 power term, we're going to keep that term outside of the sum. So we'll have 2 times 1, which is 2, times c2 times x to the 0. X to the 0 is also 1, so this is going to be coming together to be 2 c sub 2. Now everything else, both of the sums have terms involved. So we can rewrite our sums with both of these things included. So taking a look at where these are starting, the exponent on x is 1. So I'm actually going to start my sum at 1. Now, remember the n's, they have a meaning in the previous terms, and so we're going to leave n's out of it this time. And we're going to start with k equals 1 up to infinity. All this is an index variable, and we're just trying to keep the new sum, the combined sum, separate from the previous. It doesn't change any meaning for us. Now the first term is, we're going to be taking our pink term, so 3 times 2 times c sub 3, x to the first. We want to be taking that and subtracting the second term from it. So we need to represent these values in terms of k now. So plugging k equals 1 in, I want to get 3. So 3 equals 1 plus 2. So this is going to be k plus 2. And then 2 is 1 plus 1, so I want k plus 1 to be multiplying times that as well. C sub 3 is going to be c sub k plus 2. And then this is multiplied times x to the first, which I can rewrite as x to the k. And then we need to subtract the term from our second power series, our second sum. So we're going to do minus c sub 0 in terms of k's. Well, 0 is 1 minus 1, so we'll do k minus 1. And then that also is multiplied times x to the k. So we notice that both of our terms of our sum have an x to the k power in them. So I'm going to factor that out so we can clean this up. And that gives us 2 times c sub 2 plus the sum from k equals 1 to infinity of the quantity k plus 2 times k plus 1 times c k plus 2 minus c k minus 1, all times x to the k. Now, when we look at that, we did that based on what the first terms looked like. It's a really good idea to take the time to check and make sure that it works for the second terms. So let's make sure that we get the next terms that we want. So plugging in k equals 2, I'll get 4 times 3 times c sub 4 minus c sub 1 times x squared. And that matches for the terms in the sum. If you want to be super safe, check a third one. But in general, if you've done this, building it off of one, checking it on a second, and it all works, then you've probably done the changing the shifting of the summation indices correctly. So that's a way that we can combine some power series.